happy to have Rüdiger Schack here from the other London, all the way from London, UK. And Rüdiger is going to talk about participatory realism.
Well, thank you. So this is a recent classification of quantum interpretations that Adan Cabello put on the archive, on the QuantPH archive. It's you could see it as a further development of Matt Leifer's classification. So, and the main difference to Matt's scheme is in the bottom part of it. So, Adan distinguishes type 1 and type 2 interpretations, and the first one he calls intrinsic realism, and the other one participatory realism. Now, I should say right away that the term participatory realism isn't his, unlike I claimed in the abstract. It is Chris Fuchs's. So Chris Fuchs invented this term and also suggested it to Adan for this table. The type 1 interpretations, well, they're characterized by this. Probabilities are determined by real system properties. So sometimes I will refer to these as lambda, as the real system properties. And type 2 interpretations, participatory realism, well, in these cases, probabilities are not determined by real properties, by real lambdas. Now, there's some other caveat. Quantum mechanics is complicated, and there are many, many interpretations. And I'm not claiming that everything fits neatly into this classification. But it is certainly it's helpful. Within type 1, well, there are two main subcategories, the psiontic and the psi-epistemic theories. And in the first case, 1a, psi is a real property. In the other case, psi is not. It represents knowledge about some real property. And in the type 2 case, well, there is no lambda. So, but again, we like to, or Adan distinguishes between two different classes here. In the first case, psi, the wave function, represents knowledge, and one could call them again psi-epistemic. And the other one, psi, represents belief. And, well, this is set up in such a way that in the bottom category, well, Cubism fits in very neatly. This talk will be mostly about type 2 interpretations, but I'm going to, well, give some background in order to also basically motivate by talking a little bit about type 1 and why you might want to explore other possibilities. So the type 1 interpretations, the intrinsic realist interpretations, they've been very, very neatly and very clearly characterized by Rob Speckens and Nick Harrigan. In this way, Speckens and Harrigan call this assumption that of an ontological model, and it reads like this: for any measurement on a physical system, the outcome probabilities are determined by the system's real properties lambda, and that's of course just the type 1 interpretation. And I mean, there are many labels for this kind of assumptions. Often it's just called realism tout court. Also, the theories like this are called hidden variable theories. Both of them, I think, are misleading in different ways. Recently, well, I mean, this whole thing has become very popular and has been much discussed, mostly because of a set of Nogo theorems, which really start with Einstein in 1927, who showed, or who just pointed out this fact here, that if you assume what he called elements of physical reality, or lambdas, and locality, there's no spooky action of a distance, well then, psi is not in one-to-one correspondence with reality. Very simple argument. And Einstein improved this greatly 8 years later in 1935, and that was Schrödinger, which is not the EPR paper, but so this is a very different argument. And he basically proves that assuming lambda and locality implies that the wave function psi is not determined by lambda. she also mentioned, I learned this, and also the intricacies of these arguments, again from the Harrigan and Speckens paper. As I said, this distinction and the and type 1 theories became sort of a hot topic with the PBR theorem, Pusey, Barrett, and Rudolph, and then subsequent work by Kolbeck and Wenner and Hardy and others, where what was shown is that assuming lambda plus some further technical assumptions, significant weighty assumptions, implies that psi is determined by lambda. And of course, there is a tension here, and which is not surprising because according to Bell's theorem, assuming lambda and locality contradicts quantum mechanics. So, given all that, well, there have been recently some very sweeping claims in the literature. Well, no, let me just say something about locality. So I'm talking about locality here. So, well, locality, the idea that an object is directly influenced only by its immediate surrounding, was crucial for Einstein's view of physics. And he said that he couldn't see how physical laws could be formulated and tested without locality. And strangely, and in a sense dismayingly, the press, but not only the press, is full of claims that nature is non-local, and that recent Bell inequality violation experiments prove this. Here's an example in Nature, an article by Zia Merali, where she says that experiment plugs loopholes in previous demonstrations of action at a distance against Einstein's objections. There is where is it? Here it is. This is an article in the New York Times from the 21st of October last year. In a landmark study, scientists at Delft reported that they had conducted an experiment that they say proved one of the most fundamental claims of quantum theory, that objects separated by great distance can instantaneously affect each other's behavior. That's an extraordinary statement. The finding is another blow to one of the bedrock principles of standard physics known as locality, which states an object is directly influenced only by its immediate surroundings. And this is not just the press. There are also philosophers, respected philosophers. Tim Morton in 2014 wrote, what Bell proved, and what theoretical physics has not yet properly absorbed, is that the physical world itself is non-local. So what does a loophole-free Bell experiment show? Well, basically, it just shows that you have to give either locality or lambda. And if you don't want to give them a both, your choices are either lambda but non-locality. So this is the type 1 theory here, probabilities are determined by real properties, and actions at A can instantaneously influence properties at B. Or you have no lambda, but you have locality. So in this case, we have a type 2 theory, probabilities are not determined by real properties, and you have no non-locality here. So what this, of course, now tells us, well, we should look at type 2 interpretations. And that's what I want to do. I want to see and maybe show that there are interpretations or views of looking at quantum mechanics which do not make the assumption of real properties and are still coherent and meaningful and actually even natural. There's a number of theories, interpretations which fit in here. I'm only going to talk about the Copenhagen interpretation, or some version, or maybe some generic version of it, the psi-epistemic case, and about Cubism, the psi-doxastic. Okay. So in the recent talk, David Mermin gave this nice, short, clear summary of the approach of the Copenhagen interpretations, or let's say sort of some fictitious generic Copenhagen interpretation gives. So there are 3 questions here. The first is, why does the state change upon measurement? So they could be classified as three aspects of a general measurement problem. And so the answer a Copenhagen interpretation typically gives is that quantum state is a set of knowledge, and our knowledge changes when we acquire new information through the measurement. Then there's the important question, what is a measurement? Well, again, there are many versions of the answer, but often the answer is given, well, a measurement is a coupling of a quantum to a classical system. In a measurement, some microscopic aspect of a system is amplified to something macroscopic. Reversible processes become irreversible. And the outcome of a measurement, well, is a pointer reading, a mark on a piece of paper, a computer output, the state of a computer memory chip or something. Now, if you look at this, one of them is in bold, and this is actually the only one of these three that refers to users of quantum mechanics. Now, you may remember that my type 2 interpretations here, they are called participatory realism. So the participation of the user of quantum mechanics, of course, this kind of participation that I'm talking about here. So the big difference between Copenhagen and Cubism is that in Cubism, all three answers refer to the user of quantum mechanics. So why does the state change upon measurement? Well, Cubism, quantum mechanics, quantum states are states of belief, and belief changes after measurement. Question, what is a measurement? Well, here the answer is, a measurement is any action taken on the world by the user to elicit a reaction from the world. And thirdly, the outcome of a measurement is the experience induced in the user by the world's reaction. So there is this term, experience, user. So all three of them refer to the user. All answers refer to the person using quantum mechanics. So in this sense, Cubism, well, I say this to highlight two things. One is there are important differences between Copenhagen and Cubism, and secondly, Cubism takes the idea of a server participancy a big step further than typical Copenhagen interpretations. And David Mermin summarized this like this, puts the scientist back into science. So, why would you want to go beyond the Copenhagen interpretation if you're interested in type 2 interpretation or in participatory realism or in rejecting lambda and saving locality? Well, here's one key difference between Copenhagen and Cubism. A measurement in Copenhagen is an objective feature in the world. A mark on a piece of paper, for instance, an entry in a logbook. In Cubism, measurement outcome is personal to the user who experiences it. Now, why does this second idea, which looks at first maybe foreign to physics, why does it help? Well, it helps, to do with Wigner's friend. Now, Wigner's friend is, maybe the most extreme way in which one could present the measurement problem. So Wigner's friend scenario is that the friend makes a measurement in a closed lab and gets an outcome. And Wigner's outside the lab and treats the whole thing, lab, measured system, measurement apparatus, friend, everything, as one quantum systems and describes it using quantum mechanics. Now, Wigner treats the whole lab as a closed system. Of course, he's allowed to assume it follows unitary evolution, and in the end, what he gets is an entangled state, instead it's entangled between the two outcomes that the friend can possibly see and the two states of of the measured spin, say. Okay. Now, if you assume, as the Copenhagen interpretation does, and is often done, that the measurement outcome is an objective feature of the world, mark on a piece of paper, something that is actually there, well then one gets a paradox, and that's the measurement paradox in brief. There are two possibilities. Either the friend actually doesn't get, there is no objective outcome for the friend. The whole system really evolves unitarily like Wigner described it using his quantum formalism. In which case, well, you might say the friend is hallucinating something. So the friend thinks he's getting an outcome, but he isn't getting an outcome at this time. The other possibility is that the friend actually does get an outcome in there. But then Wigner's description of the whole thing as unitarily evolving is wrong. Because, of course, what Wigner should write down in that moment when the friend sees the outcome, gets the outcome, experiences the outcome, then Wigner should write down a mixture of the two possibilities, not an entangled state. So that's the Wigner's friend paradox. And Cubism, well, the paradox simply does not arise, because the friend's measurement outcome is personal to the friend. It is not an objective feature of the world. And that's all there is to it in this case. Something about language and terminology that Richard Healy already briefly alluded to. Participatory realism, well, that term is inspired by Wheeler's idea of observer participancy. Now, the term observer is, of course, is traditional in Copenhagen in quantum mechanics and has been used for many decades. But it is problematic because it suggests passive observation. Whereas, not just in Cubism, a quantum measurement is always an active intervention. A quantum measurement is an action. A quantum measurement changes the system. It's not just passive observation. So therefore, Cubism's preferred terms are either agent rather than observer, because, well, a measurement is an action, and user for the theory. Sometimes, if you want to stress the fact that, well, quantum mechanics is a tool that somebody uses, and any application of quantum mechanics is always some user's application of quantum mechanics. So now I come to the distinction I made between the two types of participatory realism, epistemic and doxastic interpretations, knowledge versus belief. So knowledge, if you use the word knowledge, again, as is traditionally done when you talk about, well, let's say Copenhagen-style interpretations. Well, knowledge suggests there's something to be known. There's something out there that's to be known. Whereas belief suggests somebody who believes. So talking about knowledge actually subtly or not so subtly pushes you back towards type 1 interpretations. And it's quite a problem for Copenhagen-style interpretations that, well, it's a slippery slope. When you talk about knowledge about what? A lot of the interpretational difficulties of Copenhagen interpretations come from that difficulty. Whereas viewing quantum states as states of belief, well, it puts firmly the agent in the center. It embraces the idea of observer participancy fully, to the fullest extent. So quantum states are states of belief in Cubism. So here we go. So in Cubism takes all probabilities as personalist Bayesian degrees of belief. And it's worth stressing that this includes, when we say all, we mean all. We mean probabilities 0 and 1. And we also mean probabilities derived from pure quantum states. So it's not just probabilities between 0 and 1, and not just mixed states. So it's all probabilities. Now, quantum states determine probabilities through the Born rule, and in turn they are determined by probabilities again via the Born rule. So if probabilities are personal judgments of the agent who assigns them, well then a quantum state is also a personal judgment of the agent who assigns it. So in the sense that, I mean, given that interpreting probability is in itself a difficult thing and a problematic thing, this starts from one very consistent, very simple interpretation of probabilities, ordinary probabilities, and just applies them without any modification to quantum mechanics. So it fits well in this. So this could almost be a starting point for a justification of Cubism. Okay, so what's personal probability? Well, it was pioneered by De Finetti and Ramsey, and given a modern form in the 50s by Savage. And it's really about action and decision theory. So the rules of probability theory are grounded in decision theory. They answer the question, how should I act? They have a normative character, not a descriptive character. And they can be derived from some version of a sure thing principle, no sure loss, Dutch book coherence. And I've shown this before, but it's just a very nice illustration of what this means. So let's just look at a very simple three-way horse race. 3 horses, 1, 2, and 3, and let's say a bookmaker offers these odds. Even on horse 1, 1 to 2 on horse 2, and 1 to 3 on horse 3. Let's say as a bettor, I make just a compound bet. So I bet 20 pounds on the 120 on the first horse, 80 on the second, and 60 on the third. So I put $260 on the table. Pounds, dollars in Canada. Okay. So now I can analyze, basically what I'm going to win or lose in the 3 possible cases. So if horse 1 wins, well, the payout is $240, and so since I put the total of 260 on the table, I have a net loss of 20. Well, that's not so bad because, of course, there are 2 other possibilities. Well, if horse 2 wins, well, since I bet $80, I get 240 back, but again, I lose 20. And if horse 3 wins, again, I lose 20. So that's not good. Of course, scenarios where a bettor loses, they are familiar from frequentist justification of probability. So in the long run, one loses, right, if one gambles. But one should point out that this is not in the long run. This is a single instance. So you do it once, and you're sure to lose $20. So what's wrong? Well, if you write down the implied probabilities for these odds, this is maybe the nice thing about this because most people are unfamiliar with betting odds and they're familiar with probabilities. Well, these 3 probabilities here, they don't add up to 1. They add up to 13 over 12. And that's just what's wrong with this. So there's a general theorem. It's not hard to prove that whenever you violate probabilities in any way in such a scenario here, you can always come up with a compound bet where you lose with certainty for every single outcome. And that's a Dutch book argument. And if you define Dutch book coherence like this, an agent's betting odds are called Dutch book coherent if they rule out the possibility of a Dutch book. And a Dutch book is just this kind of thing, where there is a Dutch book is a compound bet where actually you hand over money for every single possible outcome. So betting odds are Dutch book coherent if they rule out the possibility of a Dutch book. And now we can prove that an agent's betting odds are Dutch book coherent if and only if they conform to the standard probability rules, Kolmogorov axioms minus countable additivity. So just finite additivity. And so the Dutch book derivation therefore results in justifies the actions of probability theory and results in a theory with a normative character. It's not descriptive. It doesn't describe sort of what happens in the long run and stuff. It's just it's a normative theory. How should I gamble? And it's maybe also important to say that it does not tell you what are the right probabilities. It just tells you how the probabilities should relate to each other. So they tell you that the probabilities should add up to 1, but it doesn't tell you what the individual probabilities should be. So probabilities is degrees of belief. They're not objective, but represents an agent's personal judgments, and they're not epistemic. They're not about knowledge, but they inform action. Okay, now Born rule. The Born rule is because of the way that probabilities come into quantum mechanics. And the Born rule, therefore, has a central place in Cubism. Here, the Born rule is viewed not as a modification of probability theory, or say a law of nature, but as an addition to probability theory. The Born rule actually gives you a way of assigning probabilities in situations where ordinary probability theory is silent. So it's strictly just an addition, not a modification, an addition. It provides a connection between my probabilities for the outcomes of different, often usually incompatible measurements. And the simple way of well, seeing this tech, I mean, if you write down a quantum state, then the quantum state is, and let's say you have, then this represents your probabilities, your personal Bayesian probabilities, for the outcomes of some informationally complete measurement. Take some measurement where the outcome probabilities determine the quantum state. So that's what's writing down the state really means in these terms. It's your betting odds for the outcomes of an informationally complete measurement. Now, what the Born rule gives you is it gives you, given that, it forces you to write down certain probabilities for any other measurement you could choose. So the Born rule in this sense is really, it connects probabilities rather than setting the probabilities, or so it connects one agent's probabilities between themselves. It's got a normative character, just like the dashboard rules from before. And unlike probability theory, which can be derived from a very sort of generic requirement, no sure loss, the Born rule is empirical. It's an empirical rule. And so it tells you something. It's a statement about the character of the world. It's maybe the most fundamental statement in physics about the character of the world. It's an empirical rule. So the usual view of the Born rule is it's said that it works as a setter of probabilities, something more firm or secure than probability itself. So there is the quantum state, and the Born rule tells you what the probabilities are given the quantum state. Whereas in Cubism, there's no such thing as the quantum state. The quantum state is always ultimately dependent on an agent's priors, just like a Bayesian probability is always dependent on a user's priors. And well, there are as many quantum states for a system as there are agents interested in considering it. So what quantum mechanics gives you isn't the correct quantum state or the correct probabilities, but it gives you a way of judging whether a system of state assignments or probability assignment is coherent, consistent or not. So here's one of the maybe consequences of this viewpoint, or consequences in the sense that a statement that is needed to make the viewpoint consistent, which is maybe hard to swallow for physicists. Even probability 1 judgments are judgments. So here is a sort of Bayesian reformulation of a situation when there's probability 1. Well, Alice is certain that horse 1 will win. So, but this means in this action-based scenario that she is willing to pay $100 for a ticket that pays $100 if horse 1 wins, because she's certain the horse will win. So that's certainly the same thing. But what it does not mean here, because this is about belief and not knowledge, it does not mean that there's an objective feature of the world that guarantees that horse 1 wins. And that's, of course, that's very important for quantum interpretation, because it amounts to rejection of the EPR criterion of reality. So just to remind you of that, if without in any way disturbing a system we can predict with certainty, with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So if you think of probabilities as representing knowledge, then you would possibly accept this. If you think of probabilities as belief instead of belief, then that's unmotivated and you reject it. We're going even further. Let's look at this. A quote from Einstein in a letter to F. Reiche and his wife, 1942. So he writes, he wrote it in German, but this is the English translation. I still do not believe that the Lord God placed dice. If he had wanted to do this, then he would have done it quite thoroughly and not stopped with the plan for his gambling. In for a penny, in for a pound. That's wenn schon, denn schon in German. Then we wouldn't have to search for laws at all. Well, it's a very strong statement. So the usual reading of this is that Einstein advocates deterministic laws. The Cubist reading is, well, there are no laws. God has done it thoroughly. There are no laws that determine objective probabilities for measurement outcomes. The world does not evolve according to a mechanism. What God has provided instead is tools for agents to navigate the world, to survive in the world. So that's this. Essentially, I think this is implied if you take the type 2 theory, the type 2 alternative, seriously, and you want to come up with a coherent, consistent type 2 view, then this is what you need to accept. It's not an outlandish proposition. Here's a quote from, actually a few quotes from a paper by Donald Hoffman in Mind and Matter, who is a, sorry, I don't know what his specialty is. He works on cognition, on perception. So our perceptual systems do not try to approximate properties of an objective physical world. Moreover, evolutionary considerations properly understood do not support the hypothesis of faithful depiction, but require its rejection. So why does it, that's especially his main thesis. The argument, the evolutionary argument is this: it relates to the swift. A user interface makes one swift by not resembling the world. So he basically says that the only thing that matters for survival is that your representations of the world, your decision tools work well, they're fast. It doesn't require them to be similar to the world itself, to be faithful. And yet, in a similar spirit, concern about veridicality of a perception is a category error. The proper concern is whether perception usefully informs action. So that could be regarded as a very Cubist statement. Cubism actually in this idea is close to an old pragmatist idea, betabilitarianism, due to Oliver Holmes. So let me just back up. So what does, we all know, I mean, often it's said quantum mechanics must be true because it's so incredibly good, so precise, etc. But really, what success of quantum mechanics gives evidence for is that the theory is a great decision tool. All it tells us it works well. It works well for designing experiments and for predicting outcomes. The success of quantum mechanics provides evidence for little else. And certainly it does not provide evidence per se that quantum mechanics is a description of an objective reality. So don't think there is scientific evidence for this statement. And now to beta-abilitarianism. So this, again, this is very much Chris Fuchs's style. So here's what Cubism really should stand for, not quantum Bayesianism, because that's too narrow. It's not just about Bayesian probabilities in quantum mechanics. It's more quantum beta-abilitarianism. So quantum mechanics is a tool that anyone can use to evaluate on the basis of one's past experience, one's probabilistic expectations for one's subsequent experience. It allows you to make better bets and therefore to survive better. It's a survival tool. So the last statement says Cubist quantum mechanics is a small theory, but small in capital letters. So it does not claim to make to give you a map of the world, or just basically tells you exactly what the fundamental constituents of the world are. It only gives you this tool to survive in the world. But in that it's extremely successful, and actually in its applicability, of course, it's just exactly as successful or big as any other interpretation of quantum mechanics, because it makes exactly the same predictions. So it's just as well supported by the experimental success of science and of quantum mechanics as any other interpretation. But it's smaller. It doesn't make any claims that are, well, maybe just prejudice. And it's consistent. It doesn't have any interpretational problems, I claim. So here's something I'm often asked about. Well, it's usually phrased in the form, but isn't it solipsism? Well, no, it's not. The question is other agents. How do we deal with other agents here? Well, one thing we could write down, something that everybody who's not a solipsist immediately agree with. You could phrase it as a Copernican principle. I am not special. By one category of thought, we are agents, but by another, we are physical systems. And when we take actions upon each other, the category distinctions are symmetrical. That's what has to be true. Cubism, on the other hand, gives no third-person account of an agent's experience and experiencing. Experience is private. I have no direct access to your experience. Of course I don't. All I can infer, I mean, of course, I have access to the verbal reports that other agents give of your experiences. I have maybe some notion of how exciting you find this lecture, for instance, by looking at you. But otherwise, your experience is not, I have no access to it, or direct access. But that's not a limitation of Cubism. Just to remind you of my formulation here, it's a tool to evaluate my probabilistic expectations for my subsequent experience. Duke has a use for use, of course. It doesn't claim to map or give a faithful representation of what's going on in you. It's a small theory. So here, some justification for my claim is some form of realism, participatory realism. Or you could also call it, of course, what's the term? Instrumentalism, in a good sense. But of course, all these are just, I mean, there's labels. Cubism attempts to say strong things about the character of the world, just like physics should, physical theory. The first thing it says, experience is fundamental. So that's where we start from. So it's just a different starting point. You don't say that atoms are fundamental, or wave functions are fundamental, or the wave function of the universe, or whatever you choose, or particles. But it's experience that's fundamental. Maybe the strongest statement, agents matter. So agency is not just an epiphenomenon. Agents matter there in the center of things. There's no mechanism for how any particular experience arises. So it doesn't give such a mechanism. And actually, I mean, all the paradoxes of quantum interpretation, many of them, especially in quantum information theory, they all point to this. As soon as you come up with a mechanism, pre-existing values, you run into all kinds of difficulties. Autonomy. Now, here is something that one might confuse with irreducible randomness. But it's actually much more than that. This says any part of the world has intrinsic autonomy. So when I act on a part of the world, quantum mechanics puts no constraints on what particular experience will result. Because Cubism or quantum mechanics doesn't claim that the probability that, let's say, spin up results is a property of the world. It's just my belief. Of course, my belief doesn't put constraint on what the spin is actually going to do. So it's not like irreducible randomness, where, well, the spin was nothing determines whether the spin will come up or down, but still it's constrained by this probability 1/2, where, of course, always the difficulty is of explaining what exactly that means. So this is more, this autonomy is more. It's fundamental autonomy in the world. And the world is malleable. When I act on it, it changes. This, of course, in quantum mechanics was witnessed by my changed expectations from my future experiences. These are all things that quantum mechanics says about the world. And here's a little nod to the next talk. What's the title? 20% or 80% complete? Is that it? So I don't think any of these questions and answers have anything to do with what you're going to say, but I just couldn't resist it. So is there a fully consistent type 2 interpretation? Well, I believe Cubism answers this question with 100%. Here's something I haven't mentioned at all. Cubism, we are trying to derive quantum mechanics from a very simple, generalized law of total probability, basically a version of the Born rule that has nothing to do with Hilbert space. So can one derive quantum mechanics from this generalized law? And the answer is 100% yes, if one assumes unitary symmetry. So if one makes this rather strong symmetry assumption, then actually we can derive quantum mechanics from a very simple axiom. But that's unmotivated from a Cubist perspective. Whether you can derive it otherwise is totally, it's very hard. And finally, how much have you learned about the world? Well, then my answer is epsilon%. The hope is very little, because the hope is, of course, that we will learn a lot more. So the smaller epsilon, the better in the way. The more hope we have for the future, that it will bring exciting things. Okay, thank you very much.
So the third point, I just want to, so why say that rather than remain agnostic?
Maybe it's a prejudice. I think the reason is, I believe this because if you look at quantum mechanics and the various paradoxes you have, I mean, if you try to come up with a mechanism, then let's say the form of hidden variable theory, and that will have all kinds of undesirable properties. And so it's actually quite difficult to do that. So I think that's the reason, really. It seems the quantum formalism, the form of the quantum formalism, to me suggests this, but that's as far as it goes.
Just a general remark and then a question. So the general remark is...
Could you speak up, please?
Sorry. I thought, given your overall position, you ought to advocate quantum solipsism rather than quantum basicism, because I have, in principle, no more reason to believe that other people aren't just regularities in my experience that I can make predictions about than I do to think that there isn't really a magnetic moment of the electron, because constraints into 13 significant figures or whatever.
I mean, see, I'm not a philosopher, but maybe you can explain this to me. I mean, why is, if you're a realist, just a realist to things, let's say Bohmian or so, why is that less susceptible to solipsist criticism? Because I mean, if you're Bohmian, you think, well, okay, the whole world evolves according to this thing. It could all be evolved according to these fixed laws, these deterministic laws inside my brain. So how do I know that this is not all a simulation that happens in my brain? So I don't quite see how the solipsism idea applies any more to this than to Bohmianism or any other realist interpretation. And I think it even applies less to this one here, because since I don't postulate a mechanism, the world is constantly surprising me. Now, Bohmian, who has sort of, if you could at least in principle have sort of full information encoded somewhere, you would never be surprised. So in that sense, I think this is even less solipsist than the standard realist pictures.
Okay, but I mean, I can be a realist without thinking that any of the interpretations of quantum mechanics is right. I have no idea.
Sorry, what did you say? Sorry, I didn't hear this
I can
sentence.
be a realist without thinking that any of the interpretations of quantum mechanics is right. I mean, I just think there is a world, there are atoms,
Yeah.
and so on. But my question was about, more specific, about what you said about measurement. Because you said that measurement is an action. But if I sit next to a radioactive isotope, then even if I try not to, I'm going to be measuring it. And the projection postulate and the von Neumann theory of measurement doesn't give a good account of continuous observation. But that is just as much measurement of the quantum world as any other kind of measurement. And so I thought you should at least qualify what you said about measurement being an action.
No, actually, I'm not. I mean, I stand by this. That even that is an action if I do this. I mean, basically, what you're describing is a standard realist way of describing this decaying atom, which is sitting out there. It's a real thing, and our description of it is having a half-life, etc. And decaying. I mean, this mathematical picture of writing down the probabilities for it's decaying. They're taking this seriously, and I'm just sitting next to it, and it happens. This is not the picture I have, so I'm not qualifying it.
Surely you must think there's a difference between a measurement where I introduce an electron into a Stern-Gerlach device, and where I just plonk a Geiger counter down next to a radioactive isotope and leave it sitting there. I mean, there's no specific point in time at which the measurement is made.
Well, how about plonking down the...
And the system just sitting there, it's completely continuous. At some point, the thing's going to decay, but there's not an active process of measurement in the same way.
Well, I think it is. I mean, you plonk down the Geiger counter. I mean, that certainly is an action you take. You focus your attention on the thing.
Okay, thanks.
Okay, help me understand this restriction of scope of quantum mechanics you're proposing, because you're telling me I should only use quantum mechanics to calculate probabilities for outcomes of my future experiences. And that, compared to what most people think is the scope of the theory, is a really serious restriction of scope. So, you know, yesterday someone came to me and said, Wayne, I want your advice on how to construct a nuclear waste storage facility. And you know, calculating probabilities of decays. Should I not care about any decays that might happen after I'm gone? Would it be a mistake to use quantum mechanics to calculate probabilities of radioactive decays hundreds of years after I'm dead?
Well, my answer to that would be, I just care for my descendants in the widest sense. So I thought your answer, I mean, first of all, of course, I can use...
So according to you, I should not care about all human beings, whether they're descended from me or not?
I said in the widest sense. I mean, people come after me. I don't know.
Okay, then it seems like the list. Oh, wait. Then, all right. Then actually, okay. Then that's a widening of scope beyond what you said in the talk. So would you say really what you should say in the talk is, well, I should use quantum mechanics for probabilities of for the experience of some agent, whether it's me or not?
Yeah. Well, I mean, I said that it can be used. Any agent can use it, obviously. You see, I don't know. For some reason, I feel that this question is. I mean, it has been asked before. I don't have a terribly good answer. I just feel, to me, it feels obvious that it's just the same that I care about wild places, unspoiled wild places that I will never visit. And I would even care about them if nobody ever visited them. Somehow it feels to me like this isn't really a problem. But of course, I mean, this is why we have philosophers for this sort of thing. So basically, I would like to turn it back. I would be delighted if you could actually try to answer it in some satisfactory way.
Well, I think the answer is what I just suggested. Is that if you tell me what you said in the talk, is it really what you meant? That the scope is actually wider to calculate probabilities of things that I will experience, then we're totally agreeing.
Yeah, well, I don't want to go there because that will make a collapse, I believe. I don't want to do that.
Figure by that, and that's another question.
So I just wanted to maybe help you with that bit. So would you say that the resolution to this problem is that an agent isn't necessarily a person, right? So, in Bayesian probability theory, any collection of people who share the same utility function, or have like a joint bank account or something, could be thought of as a single rational agent. So in this sense, given that your utility function about whether the future human species survives or not is the same as theirs, you can treat you and those other people as one agent as far as that use.
Yeah, I like that answer. Yeah, I mean this sounds like William James's idea that, I mean, where do I end? And basically he includes a person's yacht, for instance, in maybe the wider persona. So again, where you end has a lot to do with where you want. So how much you include in your agenthood,
Okay,
self.
so if Baker and his friend have the same utilities, they count as one agent.
Do they have the same utility?
Okay, yeah, let them. Let's suppose that Baker and his friend do have the same utility. I mean, at least they're friends. In the case I was talking about people that haven't even met yet. So.
More on experience. When I talk about agents in quantum theory, I stress that
Could you speak up, please?
when I talk about agents in quantum theory, I stress that the agents I'm talking about don't have to be human. As far as I'm concerned, they don't have to be conscious either. So they don't have to have experiences in the ordinary sense of experience. Can your Bayesian agents have no consciousness?
Well, consciousness doesn't really matter in there, but in this is, I mean, they're users of quantum mechanics. So there are very few users of quantum mechanics in the world nowadays, and they're all conscious. At the moment, yeah.
We're working on it.
So, well, you see, but there's one. You see, what you're trying to do is really give a third-person account of an agent and of. So that's exactly, of course, what I don't do. So by treating agency and experience as my fundamental building blocks, that's where I start. So it's not. So the task is not to take physics and and ask the question, the more standard question of how can I build an agent and how can I build experience out of atoms and fields, etc. But I actually start from the other end. Now that feels, of course, for a physicist feels preposterous because the agency and experience are such complex things. But of course, that's only from that physicalist perspective that they're complex. If you start from them as your primitive, then they're not.
Yes, but if you have that perspective for the moment, then you would at least have a project in front of you of giving a kind of physical reconstruction of the quantum system that would be sufficiently cognitively complex to count as an agent,
I can.
I think you could construct such a thing which would have no experience.
I can certainly do that. I can try to construct just from computing. I can construct a system, and I expect to behave towards me in a way that would show all the signs of agency to me, and that would give me verbal reports of its experiences. But I think that's only as far as I could go.
Is that far enough for your basic agent? Would you grant that thing agency?
Well, I mean, that's not a question I would even ask, because I don't even know what it would mean for something to have real agency or be really conscious. So I think that's just the question you bypass by taking this approach, taking these things as fundamental.
So I think Lucy was next.
So I found this all pretty clear. I wonder about the text sort of shift in position from previous talks on Cubism. So Chris used to say that it was an incomplete project, and that he considered candidates for things that might actually be real, like the open space solution. I didn't hear any of that in the talk. In this talk, in fact, he also said it was a complete project. And you seemed not at any point to talk about possible real quantities in the world, so to speak.
Yeah, that's interesting. And partially I do this because I don't quite know what to think. But it's the idea I mean, Hilbert space dimension is in some sorts, I mean, for instance, is clearly more objective than a quantum state, for instance. I mean, if you have a hierarchy of things, you can, for instance, you can't toggle at a distance, whereas a quantum state you can easily toggle at a distance, for instance. So there is a hierarchy of things in let's say, their reality or their objectivity. But Hilbert space dimension, I mean, in order to be really a candidate for something that's real, it needs to have a very clear connection to a particular agent, because the idea here is that there's no well, any reality we describe is always, I mean, the realism I want to describe is always one of observer participancy. It's always participatory realism. So any candidate for what's real shouldn't just be out there in a third person perspective, because that would
because there's a question you provide an interpretation of quantum theory, and you posit some things are real. Then usually you have a particular mind as to what you have in mind as to what that reality is doing for you. So there's a Freebear model providing an ontology and the way it functions, pushing things around, so it's doing something for you. So in this case, where you admit something as being real, like for example, no space dimension, it would be sort of an internal reality for the agent. That would be you wouldn't want to admit something as being real external.
I mean, for me, that's not the project really, because isn't that the ordinary realist, or the standard or the mainstream realist project? To identify the things out there,
Right.
give a third person account of the real things out there. And the whole focus here is just to go away from that and to always to refer everything to the agent. So I wouldn't want to do that. And in a sense, the Hilbert space dimension, if anything, is less focused on an agent than, say, quantum state. Because the quantum state, I think, I mean, that's the part to treat that as personal, subjective. I think is almost it's not uncontroversial, but it's actually relatively easy to do. With Hilbert space dimension, it's harder. It's, in a sense, it's more objective. It's further away from the agent. So it almost pushes in the wrong direction.
So, you still want to say something, so you can go ahead. Are you done now? Okay, I think Bill was the next question. Bill, were you the next one?
No, I'm
No,
gonna.
you didn't. Okay, then we have this.
It was a fantastic presentation, but I'm still recovering from the shock. My first exposure to Cubism. So, two nice questions. One is, what would possibly show the theory to be false? What is the factual claim of the theory? What does it say in principle about some chunk of the world, in virtue of which, if it doesn't get it right, junk. With the bomb case, we know if there are no particles with positions, it's wrong. In the average case, we don't like what we know, what would make it wrong. In your case, it seems to me unclear what possibly would show that it's false. And the second issue is this: why couldn't we say exactly the same thing about Ptolemy's theory, and Copernicus' theory, and Newton's theory? Why isn't there a Newton Bayesianism? I mean, why should we actually take not this extreme instrumentalist, in my view, account about all kinds of attempts to understand what the world is like? Think of it as how we can understand our relation to whatever, I don't know what we related as agents, in terms of probabilities and predictions.
Well, I think we should. That's the second question. The first question was, actually, I think I disagree with the premise. Bohmianism, many worlds, Cubism, they're interpretations of quantum mechanics. So interpretations, by definition, almost make the same empirical predictions. So there's no observation that could render any of them wrong. Bohmianism might collapse from some internal contradiction or some inability to deal with relativistic effects on many worlds. So no, they're all interpretations of quantum mechanics. So they would be wrong if quantum mechanics turned out to be wrong, and that of course would
Empirically wrong, maybe, but not theoretically wrong. I mean, both theory could be wrong if there are no particles, if there are no positions. It goes beyond standard interpretation by putting extra stuff.
But that's not an empirical statement. I mean, to say there are positions is metaphysical, but it's not a statement of physics. There are no observable consequences of having particles and positions in Bohmian mechanics. So I don't think you can actually, by observation, conclude that Bohmian mechanics is wrong.
The theory is what it says about what we observe, or what we actually observe, what we could observe, what there is in the world.
Yeah, even could observe, yeah. And the other question, I mean, why, for instance, go from Ptolemaic to a Copernican to a Newtonian universe? It's just how useful they are. I mean, how much new ideas, how much new science, how much progress they create. I mean, that's just as convincing a way of saying why Newtonian mechanics is better than the Ptolemaic universe than the idea that one is closer to some real thing. I mean, this is really just this theme by Donald Hoffman. Really, what matters is how useful and how much these ideas help us to make progress and to get along in the world and to create a better world and to predict, etc. So it's not because they're closer to something real, even though of course that's the standard way of thinking, but because they're just more useful. Full stop.
Okay. That's the next question is here.
Yeah, I wanted to ask you about explanation. One thing that we typically we like to get from our scientific theories is beautiful, or at least correct, or helpful, or interesting explanations of what the world is like. And you offered us a prescription for getting by in the world and predicting our experiences. But what does that give us by way of satisfying the demand for explanation, or is that a demand you simply reject?
Well, a good explanation always, I mean, doesn't just apply to the particular thing you want to explain. It actually is more general and gives you it applies to other things. You can then use them make better predictions again. And I mean, it's actually very easy and very natural to always bring it back to this. So, when you study quantum mechanics, actually writing down wave function and sort of solving the Schrödinger equation is actually and then finding that a certain outcome has probability 0.9. That is for any physicist actually a good explanation. So why does this outcome occur? Well, here's my model. I computed it and it predicted the high probability. That's my explanation. So in that sense, even just using quantum mechanics provides explanation. Just doesn't explain the kind of mechanical or the pre-quantum mechanics kind of explication. It doesn't give you common causes, for instance, common cause explanation. So that's, but I would regard that as maybe the biggest lesson of quantum mechanics that we have to abandon. It worked extremely well for thousands of years, but quantum mechanics is a real revolution, and it still is still applicable to its own sphere. But then quantum mechanics moves beyond that and gives us new explanations, new tools for new phenomena.
So this is a question about the distinction you draw between states of belief and states of knowledge, which sounds like a legitimate distinction, but I'm worried about the slide you were talking about. So, am I right to understand that the idea here is that quantum mechanics is meant to be a theory that's for regulating our beliefs? Or you're saying it's how useful things can be for us, et cetera, like that?
Well, I prefer the formulation informs action. It gives us
so informs action, regulates. That sounds about the same.
Yeah, I mean, of course.
But why? Why think that our beliefs are well informed by the quantum mechanics that we have? I mean, normally the distinction between belief and knowledge has something to do with when you believe for the right reasons, you're closer to knowledge, for example. So are you saying that what's missing here is right reasons, or is there something else going on?
No, the right reasons are there. The right reasons are in the quantum formalism.
So
what's missing is the well, whenever you apply quantum mechanics, you just have to start with some prior beliefs, or some prior. And I mean, that's just when you write down. When you write down, you start the computation by writing down a Hamiltonian. If you do an experiment, you have a lot of complicated equipment. You have to look lots and lots of assumptions about wave functions, etc., to get started. So all these things you just don't read off the world. You actually start from a prior. Now, I think it's helpful to call this belief and not knowledge, because really that's what it is. It's assumptions. It's not knowledge. It's actually assumption. And then quantum mechanics kicks in. And then you have the formalism of quantum mechanics, which tells you how to consistently take these prior beliefs and turn them into posterior beliefs, predictions, etc. They're still beliefs, but there are many ways in which we can make them firmer. For instance, by repetition. Again, I mean, if you repeat an experiment, that's not automatically gets you closer to knowledge or anything, but it's because you have to make assumptions about repeatability, etc.
Sorry, what's the difference between firmer belief and a belief, say, that's more likely to be true?
Nothing.
So
I mean, sure. Sorry. No, I don't like that. What I meant was just predictions with probabilities closer to 1. They're firmer predictions.
Sure, but as long as those probabilities have to be constrained in some way, right? So you keep mentioning this person, the beliefs for guiding actions. I can't remember the article, but another article you might think about is Ashby and Cohen on every good regulator must be a model of the system that is regulated, right? So what this is telling me is, insofar as my theory works for me, it's actually doing a job of representation. Now, I'm not sure what necessarily is being represented, but you can't just throw away the connection between modeling and good regulation.
Well, I mean, what I'm saying here is exactly the opposite. Actually, that it's
right,
not necessary.
About regulation.
Well, that must be within some rather. I mean, it's itself a model, right? I mean, it's not in this generality. I don't think you can prove that if a model works, it must be close to something real. It's.
I wasn't talking about, well,
I mean, what these quotes claim is exactly the opposite, and they give reasons. The race to the swift user interface makes one swift by not resembling the world. It's the world is far too complex, so you need something something simple and fast that makes you that makes you make good decisions and that survive.
I agree, reasons are good things, but theorems are better things.
So Bill, was that a finger or was that something longer? Because we had a finger in the ear, didn't we?
Oh, so you want the Born rule to be constraining the agent's appropriate beliefs in these situations.
Speak up.
Why isn't the role you're given for the Born rule constraining the appropriate beliefs, giving it a kind of more objective role, almost like the chances that David Lewis said should guide the Bayesian? I mean, why the Born rule? And you're going to start. Okay, so that's.
Okay, first of all, it's not like David Lewis chances, because what the Born rule constrains is not chances; it's actually beliefs. It's not. The quantum mechanics says nothing about a particular system that sits in front of you and its probabilities. It just tells you something about if I have this model and this model and this belief, then what probability should I assign in the end? So it's really it's a consistency requirement. And the Born rule, I mean, there are two reasons. First of all, it is clearly the quantum mechanical rule that deals with probabilities in the most direct sense. We have managed to derive quantum mechanics from a totally probabilistic version of the Born rule. So it's that confirms that it has a central character. And thirdly, well, this seems to me exactly the place where something empirical comes into the otherwise. I mean, this is where physics informs your beliefs. In probability theory, I mean, it's not an abstract requirement, but the no sure loss, the sure thing principle isn't something empirical. Whereas the Born rule is about the world, it's empirical. So it constrains your beliefs and therefore enables you to do marvelous things, like build quantum computers, for instance.
So we had one last figure here.
I'm a little unclear. I've read several papers and looked around the idea of Cubism because I work with a scientist on an information theory which is very similar or the same thing, if you like, as the observer participator. And it answers questions such as the gentleman was asking and the other gentleman was asking about the rising of intelligence in observers. How similar, I mean, this is something that I didn't get out of reading the papers. So is this a commentary on Cubism or an extension or the identical thing and I just totally misunderstood the idea?
Well, it's meant to present key ideas from the real thing.
Okay. All right. Thanks.
Okay, so for time reasons we should stop here, so let's thank Rüdiger.